Thank you for the warm introduction, and Weimin, good afternoon. Today I'm going to present our work about the binary translation scheme from upgrading EVM smart contract to WASM, or we say WebAssembly. It's a blockchain paper, so let me introduce the blockchain first. The blockchain is a decentralized database, you can see, and each data block it can contain kinds of data like the address and the balance of the account. And different data block can be connected by the hash value, so it can contain, the entire database can contain some blockchain features. And the most popular one blockchain is the Ethereum. It is most popular one, and the total market value reached over 15 millions of dollars. And this because it is the first blockchain that can support the smart contracts, which is a kind of computer program running on the blockchain. It made the blockchain programmable. So basically, the Ethereum smart contracts are written in the source code in Solidity, as so in your left hand, and it can be compiled into the bytecode, so in your right hand. And this kind of bytecode is actually the program that running on the blockchain, and will be interpreted by the virtual machine called EVM. But EVM have some disadvantage by design. For example, there's no function support, and it may suffer from the DOS attack because all operation on the EVM is 215 bits. So everything running on the EVM is expensive. And some companies want to use a better runtime to replace EVM. That's what we call WebAssembly. Actually, WebAssembly is first designed for the web rather than the blockchain, but this company believes WebAssembly with better language for the web smart contracts. Yes, safer environment for executing the program, and more language support the WASM generation. And it also means the WebAssembly program has a better performance. Here are some blockchain that have moved to WebAssembly runtime. And when the new blockchain appears, the first important thing for them is to attract enough developers to write smart contracts for this new blockchain. And so they have some idea to migrate the smart contracts from the Ethereum to their new blockchain and foster the prosperity of Ethereum. And here there are some efforts. You can see if there is a WASM runtime there, and given an EVM bytecode, how to run them on the WASM runtime without EVM. So for the NIA and the Polkadot, these two kinds of blockchain, they want to compile the EVM to a WASM smart contracts, and then use this EVM smart contract to interpret other EVM bytecode on the WASM runtime. So there is a bridge between the EVM bytecode and the really execution virtual machine. So there must be some overhead there. And another competitors like the SLL and so on, they want to design a better compiler which can directly compile the Solidity source code to the WebAssembly bytecode. However, we found that there are some compiler issues in these two baselines. They cannot handle all the grammar features that introduced from the Solidity compiler, I think. And what we want to do is the EVMBT, which is a binary translation, which can directly compile the EVM bytecode to the WASM bytecode without any without any EVM support. So this is architecture of our papers. Basically, we want to extract the runtime code and the constructor from the bytecode, EVM bytecode, and then lift them to the LVMIR as the intermediate representation. Then we'll in the LVMIR to support various of Ethereum support, so that the generated smart contracts can use the Ethereum runtime and then run on the WebAssembly at the same time. And at last, we will use LVM backend like the C-Lang to generate the WASM blockchain. So there is the overflow pipeline the bytecode come in here, and we lift to the LVM assembly. At last, we generate the WASM bytecode based on the translation rules defined in this table. And I give an end-to-end case here, and if you are interested, you can see our paper for more details. So let me introduce our technical in this simple example. So in this smart contract, there are only two opicals, push and ECL. Namely, the first opical will push an immediate and a data into the stack, and then ECL will determine the value of data whether is zero. If it is, it will push the zero. It will push the one into the current stack top. To lift the stack-based language to the LVMIR, we had to use the devirtualization technology to make them to generate a register-based LVMIR register IR. And here is what we do. We will use a LVM array-nate mule as the emulated EVM stack, and use another register nate P to check the current stack depth. So the mule P is always point to the memory of the current stack top. So for the push data, this EVM opical, we can translate into these two lines of LVMIR, which first will add the register of P by 1, and then store the data from the push data to the current emulated EVM stack, which is the mule P. And for the ECL, you need to check the data on the current stack top, so we need to pop one data from the mule, which is the third line, what we do, and then we use the LVM instruction to compare the data of the C and store the result back to the stack, which is the mule P. And obviously, we can infer the operands at the compile time, so that we don't have to access too much the memory. It's a little bit like memory to register. So in here we can see the operand used by the ECL must be the data pushed by the previous opical. So we can directly compare the result of the data directly and then push the result to the stack. In this case, it has equal functionality, but it has less memory access, so it's more efficient. This is what we do for the entire papers to reduce the redundant LVMIR instructions. And for the control flow, we also do some optimization for that. All EVM jumps in the bytecode are actually indirect jump, so it's quite challenging to recover them and translate them into LVMIR. To do that, we lift all the EVM jump to the table jumps, and just like using the switch instructions, and then we will approximate all the possible destination of the individual jump so that we can ensure the translation code must be correct. And of course, if there are some situation, then we can solve the individual jump to the direct jump. We will do that using the symbolic execution. Here's just a simple case. In here, in your left, there is a bytecode, and then we can apply symbolic execution to it and calculate the destination of the jump in the 05. You can see the destination of jump must be EF because it is added by the EE plus E1. So when we finish all the optical EVM instruction translation, we implement our tool EVMBT and write experiments for it to evaluate the performance. We have a special testbed which encrypt with the EVM and the WASM runtime together, so we can replay the EVM transaction on the EVM and the WASM together, and then compare collect the trees and then compare their difference to see whether the EVMBT has the correct implementation. And we also collect two kinds of benchmark. One for the large benchmark, which consists of 2,000 smart contracts and their transactions. Another benchmark is the synthesis benchmark. In the large benchmark, we found that when we replay the smart contract of EVM and the WASM on our testbed, we can find out the similarity score of the EVM trees and the WASM trees is almost 100%. And there are still issues, I think, maybe caused by the implementation issues. But anyway, the result shows that EVMBT can retrieve high semantic correctness in translation. And we also want to mention the overhead of the EVMBT, as is the binary translation work. And in terms of guess overhead, or guess is the matrix that measuring the matrix measuring the execution cost in the EVM. And so in terms of guess overhead, we found that EVMBT introduced a low overhead, which is less than 1%. And it demonstrates a similar guess efficiency as the source code compiler baselines. But the time overhead a little bit strange because we find that it is the smart contract generated by our tools is 136 times slower. We want to know why. We guess. So we think the main overhead is caused by the WASM runtime rather than the binary translation. To prove that, we collect a synthesis benchmark which conclude 14 computation tens cases, and then we run them on the EVM and the WASM runtime to compare the time. We can find that EVMBT can achieve a speed ranging from 1.05 to 1.2 times faster, and while the baseline introduced much more overhead. So that's my conclusion. So we designed EVMBT, a novel EVM to WebAssembly binary translation framework, and we conducted extensive experiments to evaluate EVMBT by replaying the transactions on both EVM and the WASM runtime. This shows that the accuracy of our tools. And it also can generate a similar guess efficient smart contracts as the source code compiler. So there are the reference. That's all. Thank you, everyone.